We will practice machine learning. I have so many cool pictures for you and you will understand the intuition in this visual guide. But first, just one quick note. We often judge AI how smart it is, that it's not as smart as humans. But we forget that it's a machine that can think and write a lot faster than humans. Check this out. Look how fast it's coding. Let's see how fast it can code this. I just told it to write another full code for separate neural network. Look at this. Look how much code, instant. And I expect this to be a lot faster in the future. We don't have this intuition. We think AI is typing us, ChatGPT is kind of slow. But I think it can be unimaginably faster than human. And as it becomes better and smarter, it can code like huge code bases in seconds or milliseconds. And then imagine how fast it's thinking. It thought this all out in less than a second. So look at the speed of the thought process. So I'm using Qwen Coder, the latest one, Cerebrus inference and Klein extension for the coding for VS Code or Cursor. Look at this image. So red dot is circled with this red area, which is good. So this means the neural network trained. So it learned to circle a blue dot with blue stuff. So what does this mean? So it's learning classic XOR problems. So if the input is 0, 0 or 1, 1, the output should be 0, or in this case close to 0. And if input has different digits, so 0, 1 or 1, 0, then the output should be 1. So as I said, we have two inputs, so 2 inputs. It can be either of these 4 variations, and one output, which can be 0 or 1. And I grouped them here so it can train. So input 1, so the first number can be, if it's 0 and the second input is 0, then we need to have this red, which is up here, which is number 1. If first input is 1 and second input is 0, then we need to have blue, we need to have 0 here. But you can see that it's not so blue, it's a bit light blue and this is a bit light red to yellow. As you can see here, it didn't have enough time to converge all the way down to 0 and 1, so it's now hanging around 2.3 and instead of like 0, or 7.7 instead of 1. So that's why it's kind of light blue or light red. So I can increase number of epochs by 1 more, by 1 0, so 10 times. Then I can interrupt this and run again. And now it's a lot darker. In the darker area, you see how this area creeped up all the way here, and this dark area creeped up all the way here. So this is supposed to be this darkest area. I am not sure why this looks a bit lighter, but I believe that this is actually this darkest area. And you can see that we are at 0.04 and 0.96. But let me undo this epoch change, so we will stay at the lower number of epochs, and let me increase learning rate. So now it should also work now. If I increase learning rate by 10, it should have same thing as number of epochs. Same like result. But we see the result is not same. It could be due to randomness. But you see that this area creeped up as well. So actually we use 10 times less compute, we just use higher learning rate. We didn't need to do 10 times like training, we just update the weight stronger. But this can cause issues. Let's see if learning rate is too big. Instead of 1, let's put it at 100 actually. So now I'm gonna interrupt here and run again and see. Okay, this one learned also. Maybe we have a lot of parameters. And this one's like learned even better because now it's even deeper. So maybe this learning rate is not too big. But if I put learning rate 1000, now it collapsed. Now it didn't learn anything. It's too much of a learning rate. So I'm gonna go back to 10 learning rate, which works well. So if we have 6 hidden neurons, can we succeed with 4? Let's see. Now it has less neurons to learn this pattern, and it looks like it succeeded with 4 as well. Okay, let's try with 3. Let's ignore this for a moment. Let's try with 3 neurons. I want to get to the minimum successful. This one also worked. But now this is gonna be weird. I think 2 neurons will not work. But let's see. Okay, what is this? This is so weird. If we had maybe lower learning rate, you see these are very high values. I'm not sure what this is. So it looks like it did learn for 2 of the inputs, but it didn't have enough capacity to learn for the other 2 of the inputs. But let's try again. Yeah, there's just one line here. So it doesn't even have enough, like we need like 3 or 4 separations here. And I'll try once more. Yeah, we have just this one yellow separating line, which is not enough. We need at least 2, I think. So now look at this simpler case. This green is what we are trying to fit, approximate. And the red ones is the training data from this function, okay? And then blue is our neural network. But looks, what does this blue line remind you of? It looks like a sigmoid function. It looks like this. But when I remove the middle layer, now I just have one weight and activation function. And it's linear because I just have input times some weight number. So that's a linear function. There is no curvature there. But I do have sigmoid activation, so it should be a bit curved as well. So I'm not sure why it's not curved, because our linear line, that's input times weight, does get passed through a sigmoid function, so there should be some curvature. But if we add bias now there is some curvature. And you see, this learned average of all of these data values. You see, these values are pushing it a bit up here, so it's in the middle, you see. So let's go back to the straight line. So I remove bias. Now we just have input times weight, and then the result is passed through the sigmoid function. So depending if this is sigmoid function, depending on where the x is, if it's like this way, we will get all same values for y, so we will get a flat line. If x is somewhere here in this S, then we can get some S curves. Or if x is there, then we will get same y. So I'm trying to explain why, even though we have sigmoid activation, we get a straight line. And the reason a neural network learns a straight line is this is the average of all of the points. So look at this. Z range. Z is the result of weight times input. So Z range is between 0 and -1. So -1 to 0. Look at the sigmoid function. 0 is here, -1 around here. So between 0 and -1, it's flat. So wherever we land, this line will look flat. So we are not like from here to here, so there is some curvature in between. We are in the flat range. So in this case, our Z will be whatever gets inputted into the sigmoid. So it's gonna be this X. And then the output of the sigmoid will be this Y here. And it's gonna be, the Y will be like this part, so it's flat. You see here, the output is from 0.3 to 0.5. Which is exactly what I said. So you see 0.3 here to 0.5, so this part. And it's flat. I just forgot to mention, I think I did, but Z is when you multiply input with weight. So you see the input range 0 to 1, and weight is gonna be exactly learned minus 0.91. So this is the exact number. And the input is this whole range, you see this whole range of x's. Now check this out, I also have bias. So bias is learned, it's 2.9. or almost 3. And now weight is -6. So now we see that this line is more curved and it's actually more fitted to the data. It's better now. So what bias is we just do input times weight and then plus bias. And because we have this plus bias, we can have a lot larger range, -3 to 3, that goes into sigmoid function. So neural network adjusted this weight to give space for bias to push around. Together this weight and bias will push around from -3 to 3. So if you take this number in input, which is going to be 1, 1 times -6 is -6, plus this 3 is going to be -3. Or if it's 0 times -6, it's 0, plus this bias 3, it will be 3. So from -3 to 3. And that's what bias allows us to do. It expands the range that we can cover. So now we go from here, -3, there is this big S curve, up here to 3. So now we have this S curve. So this middle flat part is actually this middle flat part. And then we have a bunch of curvatures around, which is this curvature around. Now I added another neuron. So first we had like neuron, which is input times weight plus bias, and then pass that through activation function sigmoid. And whatever the output of sigmoid is, that's our output. But now we have another neuron, so both of them now have input and then weight, bias. So output of this neuron is input to this neuron. And then weight, bias for both, and activation for both. And then activation of the second hidden neuron is actually the output. So we will follow it here, don't worry. We already see that curve is even better fit now. So input from 0 to 1, you see x-axis data goes from 0 to 1 on x-axis. Weight 1 for first neuron is learned to be 5.6 and bias -2.8. And now range of input times weight plus bias is going to be from -3 to 3, almost. You can check the numbers, you can try to multiply and add, you'll see that it's from -3 to 3 almost. And then we pass these numbers through our sigmoid. And we will get between 0 and almost 1. So this is very good because you see, we get 0 to 1 sigmoid. So sigmoid actually goes from 0 to 1. So we almost cover the whole range. So here at -3 on x, we see almost 0 on y, which is here 0.05. And on +3 at x, we see almost 1 at y, which is this 0.93. So then we have these values from 0 to 1, or from 0 to 1.93, whatever. And then we have learned weight 2 -5.5 and bias 2, 2.6. So when you multiply this range 0 to 1 with -5 and add 2, you get the range from -0.5 to -2.5 to +2.3. And so the sigmoid again goes between 0 and 1 almost. So here the blue line is just this ending sigmoid function between, so you see our input is 0 to almost 1 x, and our output is also 0 to 1 almost. You see on y, 0, almost 0 to 1. And it's in shape sigmoid because the output is just going to map whatever is close to 1 to here, or whatever is close to 0 to this. So this is just sigmoid mapping. Now I want to show you something interesting. This purple is the hidden sigmoid, the middle hidden layer, hidden neuron sigmoid. So you see it's reverse. I just plotted that. Well, actually this is not reverse. Our output is reverse. You see here, this is a real sigmoid, and it's same as this hidden. And this weight is positive, so but the second weight is negative, so this second weight will reverse our sigmoid. So I can explain this easily. Look at the purple sigmoid. So here in this corner, it's a big positive number, almost 1. But it gets multiplied with a negative number. So now it becomes a negative number. So this negative number is going to be input to our sigmoid, other sigmoid. And here you can see if you have negative number as input here, the sigmoid value will be around 0.1, 0.2, etc. So we will have the other output sigmoid value close to here. So just to clear up the confusion, yes, this is number 1 and sigmoid should be high here, it is high here, but then this number 1 that was previously number 1 on X gets inverted, multiplied with a negative number. So then it becomes some other negative number, so the sigmoid goes here. It's no longer like this 1. You shouldn't look at this x-axis for this sigmoid. It's now a negative number. So I hope this transformation from 1 to this value and then this value negated and then that negative value giving low sigmoid, I hope that was clear. And if I train again, the same thing will happen. And now I added another hidden neuron, so we have 1 input, 2 hidden, 1 output. And this becomes now abstract. So this becomes maybe even too difficult to explain one by one. But these dotted lines, dashed lines, are the 2 hidden neurons. And so you see, and I just ran the training again, and it looks very similar again. So our neural network's last output layer learns to combine these 2 hidden functions to try to get this last blue function. At first, I thought, okay, so this neuron is learning downwards movement, and then this neuron is maybe learning these shapes, these curvatures, but O3 explains differently. So if you look at these numbers, the way they multiply, so with the way these weights and biases multiply these hidden neurons is this curvature on the left has a strong influence by this blue hidden neuron for these x values. So this blue hidden neuron is going to influence this curvature, while this descent and this knee, this curvature, is influenced by this orange neuron, orange hidden neuron. So this is what O3 explains. On the left half, where x is less than 0.4, neuron 1's term is the dominant one, having these values. And then neuron 2 barely moves the needle, while if x is less than 0 or more than 0.6, then neuron 2 negative term overwhelms everything and it becomes very large, and then neuron 1 is in comparison small. So this part to the right is dominated by this orange hidden neuron and its negative weight, -5, and this part is dominated by the blue hidden neuron. If we check the numbers, we will probably get, when we multiply and add these hidden neurons, we'll see that, for example, in this part, this orange times -5 gives a huge number, and so that's what's deciding these values. I think I'm getting it, but it's difficult for me as well.